The last session contains 3 talks, as I mentioned. First one is an industrial view from Keysight. Radu Lupoaie is going to talk about test and measurement and how it affects the future of 6G and the resilience of it. After that, we can hear a regulatory view from Heidi Himmanen from Traficom, how she sees the resilience as part of the 6G story. The last talk is from our sponsor, Business Finland. Pekka Rantala will introduce the 6G Bridge program and its take on resilience in his last talk today. And a few concluding words then by me later on. But let's welcome Radu to the stage.
Thank you, Ari. It's very nice to be here in Oulu. It's the 3rd time I'm here. I'm always here in winter, but it always feels somehow warm to be here, even if it's cold outside. I'm from Keysight Technologies. We are doing test and measurement, and I would like to give a perspective on how test and measurement can enable resilience, or how we can test certain resilience-related technologies as we are transitioning from 5G to 6G. I'm going to talk first about the paradigm shift that is related to measurements, to testing, as the technology evolves. Then I'm going to talk about some experiments that our research teams have done in Europe and also in Asia on network slicing, on digital twinning, and finally I would maybe have a bit of time for the key takeaways. In terms of our collaboration, so the experiments I'm going to talk about are coming from our research work in Europe and in Korea with the 6G Forum. We are planning and striving to be present across the globe, and we still hope for a global standard for 6G, but yeah, yesterday I heard some opinions that may diverge from this. It will be time to tell what will happen. In terms of the test and measurement evolution from 4G, 5G towards 6G, what we feel, what we see is that some assumptions that we had related to classical testing on the 4G and 5G architectures may probably not hold as we approach the 6G era. So some assumptions that we typically made in test and measurement was that the layers of the protocol stack were fairly independent from each other. Each layer had its own functions to fulfill. The layers were talking to each other through very well-defined interfaces. And the behavior of a specific layer was not that much dependent on the behaviors of the others, meaning that real-world factors or some cross-layer interdependencies were not really present. And finally, the network was fairly static, so we know where the G node Bs are, only the UEs are typically moving. As we move towards 6G, we are talking a lot. I heard yesterday many times, I also heard today many times the word or the term artificial intelligence. So there are going to be cross-layer independencies that are expected in 6G. We may have some controllers that are going to change the behaviors of the various layers depending on environmental factors. We have maybe the interfaces that will adapt depending on the deployments. The expectation that the network is static may no longer hold, or will definitely no longer hold, because we have terrestrial and non-terrestrial networks operating in parallel. And finally, the virtualization of the mobile network is a trend that has started in 5G and is going to become even more powerful in 6G. From a test and measurement perspective, that means that we need to have a more holistic view of the system under test, of our device under test. We need to take into considerations all these interdependencies. And the concept that we have been working on, also, for example, with the University of Oulu in some projects, is the concept of a trial network. And we can build trial networks across 3 different pillars. One of them would be more in the software domain, the foundation for a digital twin. Then once we get the first prototypes, hardware's technologies available, we can insert the concept of a hardware in the loop testing. And finally, when more and more elements of the network are available and we can build some campus level private networks, we can use such trial networks as a sandbox for these technologies. And the idea is that these trial networks should contain all the elements from the UEs to the radio access network, core network, and the final endpoints, application servers, internet elements that we want to connect to. So using these ideas, we ran some experiments in some projects, European projects. The first one was actually European, but more local to Belgium. And the concept here was to do some stress testing on a network slice in which we would like to assess for a specific use case. The use case would be autonomous driving, and we have an autonomous shuttle that would need to be always connected to some server. You may say, okay, if it's autonomous, why does it have to be connected? It needs to be connected, for example, also for some sensor sharing information, for some high priority traffic, for example, for a teleoperator, in case a teleoperator would need to take the steering wheel, to take the control. And we wanted to identify the performance limits, the bottlenecks in this trial network, and to work with the partners to find optimizations to improve the connection for this autonomous driving use case. The test setup is fairly simple, so we use the probe UE, user equipment, which was the one that would be embedded in the autonomous shuttle. We had a trial network. It was supposed to be partly with an operator, and we also did a lot of tests in our private network in Malaga, close to the University of Malaga. And we first needed to generate the traffic that would be realistic for the traffic profile of an autonomous shuttle. We use some Keysight tools for that basically generate the synthetic data with certain throughput and latency parameters. And the same tool would be used also to assess the end-to-end. Yesterday we heard from Hakima the idea of end-to-end testing, right? Of looking at a network, not only at the radio, but until the endpoint of the application. And on top of this probe UE, on which we are assessing the performance, the quality of service, we added some UE emulation capabilities. So the idea of being able to emulate the entire protocol stack of tens, hundreds, maybe up to 1,000 UEs, all the way from the physical layer to the application. So the test bed, the block diagram, as mentioned, on the top you see the probe UE, the one that is running the traffic that would be supposedly on the autonomous shuttle. Then below you see a rack. It's a tooling that can be used for UE emulation. And then we connected through the radio to a core, and we had a test slice that we used to a lab at Orange in Belgium, in Antwerp. Some measurements that we did, this is just a sample. So my colleagues ran experiments with a varying number of user equipments, of UEs, that were emulated in parallel with the traffic ran by the probe UE. And then they also increased in steps the uplink traffic from the emulated UEs in order to assess, for example, the jitter. So the jitter in the network when you increase these. I will not go too much into the details of the observations, but in a nutshell, they identified as you increase the number of UEs, you may have congestion on the radio access, so even at RRC connection setup. Then, as let's say that works well, if we are going towards generating traffic from these congestion UEs, emulated UEs, then we observe more and more bottlenecks that could further be, let's say, investigated and addressed by an operator. So this case was something that we had a device, and we thought, okay, we have a base station, a real base station, we have a device. Can we also experiment with cybersecurity? And in terms of cybersecurity, just is for the definition, so we're on the same page. We can have legitimate base stations, the ones that are part of the MNO's infrastructure. We know where they are properly configured. We know that they transmit on the right frequencies. Then we have rogue base stations, which, let's say it's a misconfigured base station or a base station that an eavesdropper got control of. This is still part of the MNO's infrastructure. And finally here, the fake base station, it's a base station that impersonates the MNO's infrastructure, but it's not in any way connected to it. So how would a device typically connect to the network? If we have a UE, a device, that device typically has a modem, and on the device you have an application, let's say TikTok, and you want to use TikTok, then the application would communicate to the modem, initializes it, and says, hey, we need to get some radio resources, we need an IP. So there is this communication to connect to the network. For every connection, of course, we have to rely on trust and reliability of the connection. And typically it's the base station, it's the network infrastructure that drives all these procedures. That was in the case when we used a legitimate base station. But if we would use a rogue base station or a fake base station in our environment, then here you see on the right-hand side that once the UE tries to connect to that network, we may capture those messages and add some malicious behavior to it, to the whole procedure. And our colleagues, my colleagues, have built a sandbox in which they experiment with fake base stations, rogue base stations, and of course in the Keysight trial network with a legitimate base station. And experiments that they did were also related to fuzzing, which I think is an interesting concept nowadays. The idea of manipulating the messages, for example, from the protocol stack on Mac or PDCP or RRC. Insert, for example, in RRC some information elements that are not really part of the normal call flow. And the idea is to identify exploits, vulnerabilities in the UE protocol stack. The experiments that they did in this case were fairly comprehensive, I would say. They tested with 10 IoT devices, not 5G necessarily, but IoT, LTE, Cat-M, narrowband IoT. And so 80% of the devices had at least one vulnerability. The worst device had 33. I don't have the names here. I was asked specifically to remove them, but they are typically devices that you may know of, with chipsets that you may know of, or you most likely know of. And some issues that they have identified, for example, after manipulating some messages in the protocol stack, for example, the modem was still alive, let's say, but it couldn't communicate in uplink, downlink anymore. It was not sending any message anymore. In that case, we could still be, were still able to reset it. In some cases, the device crashed, so crashed and reset on its own. And in some other case, it was a crash, but we had to do a hard reset, otherwise the device was stuck. So from a resilience perspective, we need to think about how these millions of devices, billions of devices we are talking about behave in live networks. And okay, what happens if we have such base stations, if we have such, I mean, rogue base stations or fake base stations? What can we do to ensure that these devices have as few vulnerabilities as possible, or at least maybe that we are stuck in the second case here, there is an automatic reset. I think that would probably be a good resilience procedure. So I talked about the concept of hardware in the loop testing, let's say, or campus trials, so learning from what 5G is able to do today. But moving towards 6G era, we may want to run some experiments that include more scale, so not only a single base station or not only 1-2 UEs. And of course, probably the first thing that comes to mind if we are looking into higher scale would be the usage of a digital twin. A digital twin of a network should ideally contain radio units or complete gNBs, user equipment, so UEs, also a way to look into the radio propagation between the users and the network, so some ray tracing tools would make sense. And then it's not only the radio part that we should ideally look into, but also the core, the virtual network functions, the run intelligent controller, maybe using some RFs, XApps. We can first use them in a sandbox like a digital twin before deploying them in a live network. And we look at the digital twin from a test and measurement perspective as a sandbox where we can first assess the performance of certain technologies before deploying them in the field. But of course, they can also be used, for example, to generate synthetic data for AI training or for AI model validation before deploying it. And in this example that I'm going to talk about, this was an experiment that we did with the 6G Forum in Korea. 6G Forum is an organization bringing together academia and industry doing research on 6G. And here we wanted to assess the impact of extreme MIMO, which is a big topic, extra large MIMO, extreme MIMO that is discussed now in the context of 6G. Going up in frequency means that we can increase the number of antenna elements and we can get narrower beams and serve more users from the same radio resources from the same radio unit. So how do we build a digital twin? Well, here, of course, you may use satellite imagery. You can get, I know the city of Helsinki, we had some experiments there. They had some very nice 3D maps available with very rich metadata about the buildings. Here, the experiments was on the Yeouido Island in Korea, and we didn't have such high-quality digital maps. What we did was to work with a company that flew a drone around and collected high-quality data, images, to build the 3D model on the right. So on the left, you see the points between which the drone was flying on this island. On the right is the output of the information that we collected from the drone flying around. Then once we have this foundation, the map on which we build a network digital twin, the next point is to create the scenario. So where is my base station? Where are my UEs? And in this case, we can place the UEs on the map. We can define what type of antennas they have. We can place the gNB with the height of the mast, for example, the type of antennas on the gNB, on the radio unit. And in case you need some mobility in your scenario, we can also consider the mobility routes of the UEs around this gNB. And now that we have defined the scenario and we know where we have the map, we have the UE placement, we have the base station placement. In this case, in order to assess the impact of increasing the number of antenna elements and getting narrower beams out of our base stations, we created a few scenarios with 20 and 40 UEs. For simplicity, in this case, we use static UEs. And in order to see the capacity gains from using this beamforming technique, we limited the bandwidth that would be allocated in the network. So we use a bandwidth part of about 20 megahertz, and we had up to 8 users that were connected to the network through this 20 megahertz bandwidth part. Here it's an interface of the experiment, and on the big picture on the left you see this plaza in which the UEs would be placed. And on the right hand side you see the video quality. So the idea was that we wanted to assess the quality of experience. How does the quality of experience for a user improve when we go from 8 to 64 to 256 antenna elements in the radio unit? And one thing you could do is to look at the video for these individual users and really check, okay, do I see dropped frames? Do I see blurred and lagging video? Or I can look at some proxies, and I'm going to talk about that in the next slide. And on the lower corner of this picture, we had some visualization data of the throughput in the network. We had an estimate of the energy consumption, which was based on a model of the PRB, of the resource blocks that were allocated in the network. And we could also see the packet error rate. So I mentioned that you probably sometimes can't really watch all the videos of the 20 or 40 users. In this case, we used the channel quality information that was reported by the UEs as a proxy for the quality of the video that they would be able to watch. And the greener the block there, so here this is an example for the 40 UEs. Each of those blocks represents the CQI for a UE, and the greener the block, the higher the CQI. When it's towards red, if you would watch the video, I mean, you wouldn't be able to watch the video. There is no bunny in the video. And here it's a high-level depiction of the results. So in the first graph, you see the results for 8 antenna elements, where you see that there was no way those users could watch the video. As we move towards 64 antennas, it was a bit better. So a couple of users could see the bunny. And then if we look at the last graph on the right with 256 antennas where we had narrower beams, in that case, there is a significant amount, more than half of the users were able to watch a fairly decent video. And finally, so from our perspective, the idea is that it's best to employ complementary tools in order to assess technologies depending on the stage in which we are with the technology development. If it's a software-only area, simulations of our process, or if we already have some prototypes, or we are already ready for deployment. And we can intertwine these tools and have a continuous innovation, continuous development, continuous test process that we can use. I think a digital twin can always be enhanced on fidelity or scalability axis. It depends on how many resources, how much resource you have available, and if it's really necessary to go on each of these axes. And yeah, that's pretty much all from my side. Please.
Yeah, thanks a lot for the digital twin demo. My only question is that what were the assumptions on the scheduler when you were actually reporting that everyone can watch the video? Because it's not just a function of the CQI, but it's also the function of the packet buffer and how the UEs get scheduled.
Okay, so in this case, we did have implemented and running in real time the stacks of the UEs and the base station. We do assume some level of ideation in there, so it's not a real Nokia base station scheduler that we have in that case. What we wanted to show there, if I have a limitation on the number of PRBs up to the PRBs that fit in 20 megahertz, do I get more capacity in the network by using the beamforming? So there is not that much detail into that. We are happy to work with you if you would like to plug in your, let's say, a digital representation, for example, of your scheduler in a digital twin. But in this case, it is something that we developed on our own.
Thank you very much for this very important also piece of work. I have a question. You know, in the academia, we have a lot of work ongoing trying to build simulators. We have a lot of assumptions on the radio layer. What would be your advice to optimize our effort and join forces in this time where we need to validate different concepts in 6G? Thank you.
Thank you for the question. That's a very good question. The way we look currently at the radio part, I think the radio is important for the people that work on the radio, more or less. In this case, what we have used is a ray tracing tool that can be used in simulation only. And then we have the capability of using the same scenarios on a hardware channel emulator if you would like to move from software to hardware. So if you have some prototypes, for example, and you would like to test first your prototypes in software and then move to a hardware environment, you can reuse to some extent the same scenarios that you can create. And we think that's important in my pillars, moving from software to hardware in the loop to campus trial networks. And I think it's important to be able to have some connection between these three stages. I didn't have anything here on my slide, but you also mentioned academia and collaborations. We are part of the 6G Sandbox project. It's a 6G SNS project, and there is infrastructure connected, for example, Malaga. There is infrastructure here with the University of Oulu. There is in Athens as well as in Berlin. And for the first half of next year, there are some trials organized. So if you would like to bring your own device, for example, for some NTN testing, I mean NT-NTN integration on FR3 or on RIS and time-sensitive networking, these are the 4 topics. You can bring your own technology, device, algorithm, and we find a way to plug it into this infrastructure, for example. I hope it answers your question a bit.
Hi. Thank you. Very interesting presentation. Also to get a feeling of how your digital twin works. I had one question. So in your digital twin setup, is it also possible to emulate multiple gNB with core network elements where you take out certain gNB and see the impact and things like that?
Yes. So that is a possibility that we would like to offer. In this specific case, I would say that it's more a radio digital twin. But as I mentioned, we have capabilities to add. I mean, here it was simplified, right? We had only one gNB. But having more gNBs, more UEs are things that we can do. And if you would like to bring your own multi-gNB stack, for example, that is also something that we can discuss about. I think there was a question there.
I had one here.
Yes.
Thank you for the interesting presentation. I took interest in the part where you showed the crashing of the modems with the rogue base station. So one question, did you go any further than that? Were you perhaps able to access the operating system through the rogue base station, or was it only crashing of the modems?
The results that we have so far are the ones that I mentioned, so they were not really going that much up the protocol stack, but some of the work we've been doing is to work more on this fuzzing algorithm. So fuzzing that we did at, so the mutation, let's say, of some elements in the messages, and to assess the impact on the modem. And they were on the 3GPP defined part of the protocol stack. So what is, let's say, on the, it was in MAC, in PDCP, and in the radio resource control on RRC. So we didn't really go further up.
I was looking for like stuff like possible data exfiltration or stuff through hacking of the modem, but I think you answered my question.
I will also tell you that I'm not the most educated person on this topic. I just presented you some of the results that we have, but I would like to, maybe we can talk about it and go into more details. I can connect you with some of my colleagues if you want to talk more about that. Thank you.
Thank you very much.
Thank you.